Okay, we continue our lesson here. So we go for question 5.20, modify problem 5.14 for a free stream turbulent level of 1%. So I think for those who do the CFD, so sometimes they are very particular with the turbulent level. Okay, normally for the low turbulent level, so maybe they use maximum 1%. So if the high is might be around 5 to 20%. Okay, so and then we go for the problem 4.14. For stagnation boundary layer flow, U equal kx, estimate the position Reynolds number where transition first occur using the method of Michel by equation 3.38. So we already answered problem 5.14. So and then here the simplification. So this is the value of the equation for beta, and then we know that the beta is equal to 1, and then the m is also equal to 1, and then from the table we could get this value, and then we substitute into this one, and then we could get the value of 0.29 0.29235, and then we just simplify the idea here because the value u is equal kx, so we substitute here, so we could get it is equal to 0.29235 square root nu over k. So and then to solve problems or to estimate the transition with turbulent intensity, so we need to use the equation of Van Dryers and Blammer theory. So the equation is like this. So and then in this equation we have the value of t here. So the value of t is actually the turbulent fraction. So if the turbulent intensity is 1%, so we need to substitute the value of t equal to 0.01. So here we have beta and m is equal to 1, theta star is here, and eta in terms of delta is 2.4. So here 2.4 here is actually from the table here. So we could get the value here, and then we get the eta is 2.4 because we need to get the value of 99%. Okay. So the condition occur, U over U is at 99%. So this is the condition of the boundary layer. That's why in the table, we take the value of eta delta here is 2.4. So we just take the value here, 2.4 here. So this is 0.99055. Okay, so this is what we get from the table 4.2. So and then we know the value of Reynolds number theta is u theta nu, and then we substitute the value of u here. So and then we substitute the value of theta. So this is the value of theta, and this is the value of u. So and then the nu here is remain. So and then we could rearrange this equation into this term. So I hope you understand to convert the Reynolds theta into 0.29235 square root Reynolds, and then we could rearrange this one by this. So and then we calculate by using the idea of Michel, and then we could estimate the Reynolds number transition is occur at 9.225 times 10 to the power of 9. Okay, so this is solution. This solution is actually without a free stream turbulent. So then if we want to calculate with a free stream turbulent, so what we need to do is we need to take the value of t is equal 0.1. So and then because it is stagnation flow, So first, we need to calculate the value of theta square over nu by using the Twitch equation like this one. We substitute the value of u equal kx, and then we could simplify it as 0.075 over k. So and then we do the differential, differentiate the value du dx is equal to k because we want to solve the value of lambda. And then we could calculate the value of lambda, which is equal to 0.075, means the value of lambda is greater than 0.04. So it is important to know about this one because the Blummer equation is actually can be used only if the value of lambda is greater than 0.04. So and then this is the equation. We substitute the value. The most important thing is we substitute the value of t there. So the amount of t is 0.01. So and then we could calculate. We found that the z because it is z with a power of 2. No, because we have the square root number there. So we have the z here. So we have another z here. So mean z will become with a z square. Means that we could get the Reynolds number 1203 and negative 1534. So for sure we take the positive value. And then the value of Reynolds number transition is can be estimated as 1.447 times 10 to the power of 6. So if you see here, so the transition from a laminar to turbulent will occur early if our free stream velocity has a turbulent intensity of 1%. So this is 1.4 10 to the power of 6, but without anything, without turbulent intensity, so the Reynolds number transition will occur around 9.2 times 10 to the power of 9. And then we go for the next question. So the nature of the question is still the same. Modified problem 5.15 for a free stream turbulent level of 1%. So this is the question for problem 5.15. So it's about the separating a flow where beta is equal negative 0.19. So almost all this data is given from the is already discussed in previous tutorial. So and then we go for the Twitch equation here. We substitute the value of u equal kx to the power of m. So here please be careful. In previous calculation, we have beta is equal to 1 and m equal to 1. So that's why we use u equal kx, because if we see notes from the previous lecture, we write u is equal kx by to the power of m. So because m is equal to 1, so we just use kx. So but in this situation, we have m is equal to negative 0.09043. So means that our velocity, local velocity, the equation for the local velocity will become kx to the power of negative 0.09043. So and then we substitute into the Twitch equation here. So and then you could solve the problem of this one. So and then we need to calculate the value of lambda. So and then the lambda here, we start with the du dx. So and then we could calculate the lambda, and then the lambda is negative 0.0743, which is less than 0.04. So here we need to make some decision. We make a decision because the value of lambda is less than 0.04, so we can use both type of correlation. So we have one is Blummer, so and then another one is Dunham correlation. Oh, okay. So I mean Okay, so we go for the we have two equation that can be used. One is Van Dries and Blammer, and another one is Dunham. So we go for this the Blammer first. So we have this equation Reynolds number theta, and then we substitute the value. We could get this one, and then we could have this term. So and then it is equal to the Michel 2.9 Reynolds number 0.4, and then we could calculate the Reynolds number as 1.73 times 10 to the power of 6. So this is without free stream turbulence. So this is actually free stream turbulence without any turbulent intensity. So and then we need to calculate the value of eta delta here. So we check table 4.2. Okay, so because we need to calculate the value of 0.99. So the value here is quite big. We have 0.994 and we have 0.97. So that's why we interpolate the value. So we get the eta delta here is 4.874. So and then we use the Van Dries and Blammer. So this is the equation. We substitute the value of T here. So and then we could calculate the Reynolds transition is 1.71 times 10 to the power of 5. So and then if we want to use a Dunham correlation, so this is the equation. So we have another parameter to be defined, which is the lambda. So we start with the theta star. So from this equation, so you could check from the table to get this value, and it is equal to this equation. So we could calculate the value of theta. We could get this one, and then we could write as theta square over nu is equal 0.7536 x over u. So and then we have u equal kx negative 0.09. So we have u dx, and finally we could substitute into this one. And then we could get it is equal to negative 0.0681. Then we substitute into the equation of this one. So and then we could get the Reynolds theta transition is 447.5. So and then we for separating flow from the previous equation, we could get this one. Now we could calculate the value of Reynolds number here. So and then it is equal to 2.66 times 10 to the power of 5. So from this answer, you will get 2.66 times 10 to the power of 5, and with another method we get 1.7 times 10 to the power of 5. So only 1.6 10 to the power of 5, and this is 2.6 times 10 to the power of 5. So means that the difference is not so big. So actually both estimation can be used. And then I hope you could understand that the transition is occur earlier because we have the turbulent intensity in our free stream velocity. So and then this is actually the notes for separating flow. The lambda can be determined by using this equation. So this is the quite common equation, and also the theta square over nu can be calculated by using this equation. Now we will go for question 5.25. So it is about the effect of surface roughness on transition. So normally we could say that beside of Reynolds number means the value of density, the speed, the length of the plate, for example, and the dynamic viscosity. There are a few parameter that could influence the flow. Okay, the most common one is the surface roughness. So means the quality of the surface. The surface roughness in this term can be divided into two. One is actually the natural surface roughness, because how hard you polish a surface, so for sure it will have surface roughness. So mean it still have hill and valley on the topography. So the surface of that one will more or less will influence the flow. And then sometimes we create our own surface roughness. It is also known as the artificial surface roughness. Sometimes people call it as a vortex generator. They will have a dimple, for example, for a golf ball, and sometimes they will put disturbance. So any kind rectangular block and so on and so forth on the surface to trigger the turbulent flow. Okay, so in this situation, so it's very simple. It put a wire, because in this idea is actually it is easy for us to change the location of wire. So the wire here is perpendicular to the flow here. So means that we could change the location to control the turbulent flow. So let's say we have air at 20 degrees Celsius and one ATM flows at U equal 12 meter per second. Past a smooth flat plate, it is desired to trip the boundary layer to turbulence by stretching a 1 millimeter diameter wire across the plate at the wall, where will transition occur if the wire is placed at x equal 1 meter. So the question is, if we put the wire at x equal 1 meter, so the transition will occur or not. Because sometimes if we put the wire is too late, maybe the transition is already occurred. But if we put a wire is too early, maybe the flow, the laminar flow will flow on the wire, but the location is not so strategic, means that it cannot change. It cannot change the energy of laminar flow, and it still remain laminar flow after flowing on the wire. So this is the situation. And then what wire location X will cause the earliest transition in this one. So and then we estimate the flow instability, because we are dealing with a flat plate. So the beta here is equal to 0. So and then we could calculate the value of theta star. It is equal to 0.4696. So and then from here we could calculate the value of theta, and then we could see from the table actually at the same time, and then we could change into the Reynolds number is here. Reynolds theta is equal to 0.6641, Reynolds number x equal to 201, and then we could calculate the Reynolds number x is equal to 91,000. So means that the idea is at Reynolds number 91,606, the flow start to become unstable. So this is the idea is it is not worth for us to put a wire before Reynolds number 91,000, because if the flow is stable, as I said, as we discussed in today's in the first lecture, the stability means the capability of flow to return back to its original position or to its original condition. So mean if the flow is stable, let's say we have a stable laminar flow. If you put anything on it, so maybe it become a little bit chaotic, but it will back to normal flow. So means that it is worth for us to know the stability, because it is chance for us to change the behavior. So we estimate the transition. So we use the Michel. We just go a little bit faster here. So we could it is equal to 2.9 Reynolds number to the power of 0.4, and then we could estimate it is around 2.5 times 10 to the power of 6, or you could write as 3 times 10 to the power of 6. So means the flow start to change to fully turbulent boundary layer. So from this data, what you could understand is it is too late for you if you put the wire at around 2.5 times 10 to the power of 6 Reynolds number, because the flow is already in turbulent, means that it is waste for you to put a wire on that region. So mean at least here you could estimate the best region to put the wire to enhance or to make the turbulence occur earlier. So and then for 20 degrees Celsius at 1 atm, we know the kinematic viscosity of air is 1.5 times 10 to the power of -5, and the estimation length is x is equal to 1. So and then if we calculate the Reynolds number at x equal to 1, we found that it is still 8 times 10 to the power of 5. So we assume it's still a laminar boundary layer. So because we found that the transition, mean the changes from laminar to turbulent, occur at this one. So means that at this value, so the flow is remain laminar. As I said, in normal practice, we could say that it's 5 times 10 to the power of 5 is a normal transition, but in advanced condition like this one, if you do research, so you need to calculate everything about your boundary layer transition point. So and then we know that delta star is 1.72x over Reynolds number, so we could get this from the Blasius exact solution. So please refer back the equation for Blasius. So we just use the equation, so we get it is 1.923 millimeters. So at this position, a wire of diameter k equal 1 millimeter has ratio of this one. So first we need to calculate the ratio k over delta star, and then because it is okay for us not to use the unit of meter because we are calculating ratio of this one. So mean if both parameter use the unit of millimeter, so you could just divide 1 over 1.923, so you would get the ratio of 0.52, which will certainly cause early transition. So this idea is actually based on so we have graph here. As I said, it is not easy to predict the to calculate the effect of surface roughness on boundary layer, because surface roughness can be anything. So it is we don't have an exact equation to calculate to predict the behavior. So what we use here is actually the prediction of the by using data from the previous researcher. So for example, one researcher plotting or make correlation of the Reynolds number of rough and surface with the k over delta star. So we calculate the value of k over delta star. So we found it is 0.52. So it is might be around this. Okay, I'm sorry, 0.52. It is between, this is 0.5. I'm sorry, so this is 0.52. So and then the value is almost 0.4. Okay, so means that according to the graph, if the k is equal to delta star equal to 0.52, so the ratio of the Reynolds number rough over smooth, it is around 0.4. So so and then if you use this one, so if the this is for incompressible and this is for compressible. So however, if you see this line, so this line is also for the incompressible, you will find that the k Okay, if the K over delta star is 0.5, so if you stretch this line, you will get it is intersect at 0.4 there. So actually this line is this line how in you know in we compact the x-axis here. Okay. So and then here we just estimate the transition Reynolds number is 3 times 10 to the power of 6. So means that the Reynolds, because the ratio here is 0.4, so it is okay for you to use 2.6 something. So in this calculation, let's say if I take it's 3 times 10 to the power of 6, so we could estimate the Reynolds number transition for the rough, which is 0.4 times Reynolds number smooth. So then our estimation for the transition point location with the wire trip is by this one. So mean after you get the location of Reynolds number transition here. Okay, so and then we could reverse calculation. We could calculate the location of x. So mean the calculation of x here is 1.5 meter. So means that transition will occur at x x equal 1.5 meter by putting on wire on the plate. So in this situation, we could assume that it is advantage for us to put that wire, because that wire could change the flow into the turbulent flow. And for smooth plate, transition usually occur at Reynolds number 3 times 10 to the power of 6. So if we don't put any wire, and then we assume that the transition is occur at 3 times 10 to the power of 6, so means that the transition will occur at 3.75 meter. So means that it is advantage, because we could create a turbulent flow earlier compare if we don't put any wire on the flat surface. So however, this question is very limited actually. It is depend on the situation, because they are using a few numbers, a few ratio that are being investigated earlier. So means that if you are doing research in boundary layer, that it is worth for you to do the experimental work instead of 100% simulation, because sometimes we need to observe the phenomenon before we could predict it, or before we could simulate it numerically. So and then the earliest transition from figure here, when the wire costs the lower possible value of Reynolds number. So this is the second question actually, because we want to calculate what is the earliest point that we could create the transition. So here, this is the graph again from the previous researcher. So we found that according to this data, maybe we could assume that the earliest one, or the smallest one, is start at this point, means that the K over delta star is equal 0.8. So and then at K equals 0.8, so the value or the ratio of the roughness and smooth Reynolds number is 0.1. So means that if the ratio is 0.1, so we could assume that the Reynolds number for smooth is 3 times 10 to the power of 6, and the Reynolds number for rough surface is 3 times 10 to the power of 5. So and then this is a flat theory. So we just use this one. It's come from the idea of Blasius actually. So we have K over delta star is 0.8 K square root Reynolds number rough over 1.7 X. So this is actually the value of delta star. Okay, so now the value of X is 3 398K, and if K is 1 millimeter, so which is 0.001 meter, so the value of X is 0.398 meters. So mean a 1 millimeter wire placed at X equals 0.398 meter would cause transition almost immediately downstream. So this is the idea to estimate the earliest place of the wire to which could change the flow from laminar to turbulent. So and then we try to solve this one. So repeat problem 5.25. If the free stream turbulent level is 1%, so it's still the same problem. The flat plate with a velocity of u equal to 12 meter per second, but now the idea is the free stream turbulent level is 1%. So and then we calculate, so we found that the Reynolds number is turbulent, Re equal Ux over nu, so we substitute the value, so it is 8 times 10 to the power of 5. So and then we calculate by using the idea, okay, from Van Rys and Blammer. So we have this equation, we substitute the value of t equal 1%, 0.01. So and then we get the transition is 5 times 10 to the power of 5. So and then we found that if the free stream velocity has the turbulent intensity, so mean the transition is already occur at Reynolds number 5 times 10 to the power of 5. So means that the location of here, the location of x equal to 1 meter here is actually too late. So the transition has already occurred at 5 times 10 to the power of 5. So and then we repeat problem 5.19 in this question. If the free stream has a turbulent level of 4%, find the estimated transition Reynolds number by two different methods and compare. So this is problem 5.19. So based on the previous calculation, we know that u is equal kx to the power of 1 over 4. So the beta is equal to 0.4 and the lambda is equal to 0.05. So because we calculate the value of lambda is equal to lambda is greater than 0.04, so means that we cannot use the Dunham estimation, because the Dunham estimation is only valid for lambda less than 0.04. So and then here for the turbulent intensity more than 1%, so we are advised to use the estimation by using Schmidt and Henningsen with equation 5.47. So we have this equation, so we substitute the value of Reynolds number, then we could get it is around 90,000 to 120,000. So here normally people will take the average one, so it is okay for us to say that if the turbulent intensity is 4%, so the transition can be estimated occur at 1 times 10 to the power of 5.